Welcome to Diploma 3rd Sem Electrical LMSE content for subject DC machines and alternators. Unit 2 Performance of DC generator. In that we are studying session 14 Efficiency and voltage regulation of DC generator. In this session we will study losses in DC generator, different power stages in DC generator, efficiency of DC generator, voltage regulation of DC generator, and some simple problems. First, to study the efficiency of DC generator, we need to know the losses in the DC generator. The efficiency itself gives us the idea how efficient the DC generator is. How much given input is converted into output. How efficient the machine is. We get that idea by knowing the efficiency of generator. To study the efficiency, we need to know the losses. The various losses in the DC generator are copper losses, iron losses, and mechanical losses. Copper losses are the losses taking place in the copper area of the machine. That is, the armature copper loss in the armature winding, shunt copper loss and series copper loss in the shunt field winding and series field winding. Armature copper loss is given by armature current IA square RA. It is given by IA square RA. As armature current is variable, it varies with the load. This loss is known as variable loss. This loss varies with the load. The armature copper loss will be around 30 to 40% of the full load loss. Shunt copper loss, it is the loss taking place in the shunt field winding of the generator, and it is given by ISH square RSH, where RSH is the resistance of the shunt field winding. As the shunt field current is constant, this loss is also treated as a constant loss. And another one is series field copper loss. In series generator, and it is given by ISC square RAC, and it is also a variable loss. The shunt and series copper losses are the field copper losses. The total field copper loss will be around 20 to 30% of the full load losses. The next one is iron losses. The losses which are taking place in the iron part of the machine, that is, they are also called as magnetic losses. They are also called as core losses. The first one is hysteresis loss. Hysteresis loss, which is the loss taking place in the core of the armature due to the continuous reversal of the flux in the armature core. When armature core passes in the magnetic field poles, when it passes through N and S pole, the flux in the core reverses. Due to the reversal of the flux, the heat is produced. That heat loss, that will make some power loss. This hysteresis loss is given by Steinmetz equation, that is B maximum to the power of 1.6 F V watts. This hysteresis losses depends on the grade of the iron and volume of the core. To reduce this hysteresis loss, silicon content steels are used in constructing the core of the generator. Another core loss is eddy current loss. Eddy current loss is the loss produced due to the eddy currents produced in the core of the armature. The eddy currents are produced when armature rotates in the magnetic field. The EMF also induces in the core and current is induced. These currents are called as eddy currents. And having a small resistance, this current will make a larger effect. These losses depends on the thickness square of the core. To reduce this loss, the cores are to reduce the thickness, the cores are made with the help of laminations. By using the laminated core, the loss due to eddy current effect can be reduced. Both these losses, hysteresis and eddy current loss, collectively, they are core losses. They are constant in all the generators. These core losses or iron loss or magnetic loss are around 20 to 30% of the full load losses. Another one is mechanical losses, which are taking place in the mechanical parts of the generator. That is friction loss at the bearings and air friction loss around the rotating part. These friction and windage loss together, they are called as mechanical losses. These losses are around 10 to 20% of the full load losses. So these are the various losses which are occurring in any DC generator. Certain terminologies we are using along with these losses, that is stray losses and constant losses. The stray losses means magnetic loss plus mechanical losses together is called as stray losses. Another term we use usually is constant or standing losses. Shunt field copper loss plus stray losses are collectively called as constant loss. So with this idea, we can calculate the total loss in the DC generator. For shunt and compound generator, the total loss can be obtained like this. The total loss equal to armature copper loss plus constant losses. WC is the constant loss. Armature copper loss is given by IA square RA plus WC. IA is armature current, that is I plus ISH square RA plus WC. Armature copper loss are the variable losses. So hence the total loss in the DC generator is given by, it is the sum of variable loss plus constant losses. Like this we can calculate the total losses in the DC generator. The different power stages in DC generator. You know that the input to the DC generator is the mechanical power and we get the electrical power at the output terminal of the DC generator. This can be divided into various stages. That is, the mechanical power input is given to the armature. Out of that, some loss takes place in the armature itself. That is called as magnetic loss and mechanical loss. That is iron and friction losses. Out of the input minus this magnetic and mechanical losses, we get the remaining power is supplied to the armature winding. That is, the remaining power is converted into electrical power in the armature. That is given by EG and IA. So much of watt is power developed in the armature. That is called as stage B. Stage A, we give the mechanical input. Out of that, some loss, that is iron and friction loss, takes place. The remaining loss is converted into electrical loss. When electrical power is developed, that is EMF is induced in current flows through the winding, and when current flows through the winding, copper loss takes place. Subtracting the copper losses from the power developed in the armature, we get what is the total output power at the output terminal. This is the power available at the output. That is stage C. That is what is a useful power which can be connected to load. These are the various stages of the power in the DC generator. Based on this, we are calculating a different efficiency for the generator. Now we will see the three different generator efficiencies we usually use based on the power stages what we have studied, from mechanical power applied to the generator, to the power developed in the armature, and to the next, the actual power or output power available at the output terminal. Based on those three stages, A, mechanical power, B, power developed at the armature, electrical power developed at the armature, and C, output power available at the output terminal of the generator. The three efficiencies we generally use are: number one, mechanical efficiency denoted by eta M, that is given by B by A with respect to that power stages diagram. B is, that is total watts generated in armature divided by mechanical power supplied to the armature. The total power developed in the armature is given by EG IA, and mechanical power supplied is output of the driving engine, that is the output of the prime mover is the mechanical power supplied to the armature. The second efficiency terminology we use with generator is electrical efficiency, that is given by watts available in load circuit, that is actual output power divided by total watts generated in the armature. The watts available in the load circuit is Vi divided by the watts generated or total power generated in the armature is Eg Ia. Another one is overall efficiency. It is also called as commercial efficiency. It is total output of the generator divided by total inputs supplied to the generator. That is total watts available in the load circuit divided by mechanical power supplied. The overall efficiency is given by mechanical efficiency into electrical efficiency. For a good practical generator, this value is as high as 95%. But one thing you need to note here is, unless specified, the efficiency of generator means it is commercial efficiency only. Even in the problems, if you have been asked to calculate mechanical efficiency, then you have to calculate. If you have been asked to calculate electrical efficiency, then you have to calculate. unless otherwise it is not mentioned, only efficiency of generator means it is overall or commercial efficiency. This is commonly used terminology for the efficiency. Next, condition for maximum efficiency of DC generator. That is, when the generator gives maximum efficiency, that is at what load it delivers the maximum efficiency. That helps user to apply the load on the generator at that load only to make use of the machine more efficiently. Right? The efficiency is given by output by input. Again, right? The output of the generator is Vi. Generator input is output plus losses. The output is Vi plus losses are variable loss plus constant loss, that is Ia square Ra plus Wc. So this equation can be written as where Ia is I plus Ish. The equation becomes Vi plus I plus Ish square whole square Ra plus Wc. Because armature current is load current plus field current, shunt field current. If Ish is negligible as compared to the load current, because Ish is too small compared to the load current, so then Ia will be equal to I approximately. So then the efficiency, in efficiency equation, by substituting these values of output and input, we get output Vi, input is neglecting Ish. Vi plus Ia square Ra plus Wc, that is Vi plus I square Ra plus Wc. That is neglecting Ish, Ia is approximately equal to I. The equation will become like this by dividing numerator and denominator by Vi. We can simplify this to this way. By this equation, we can say this equation will give us the maximum value when this term is equal to 0. IRA by V plus WC by VI is equal to 0. That is the condition for maximum efficiency. Now the efficiency is maximum and denominator is minimum, obviously. In the denominator part, when this is equal to 0, then we get the maximum efficiency. To make that equal to 0, we have to differentiate that part with respect to the variable, that is load current I. Differentiating this term IRA by V plus WC by VI with respect to I and equating that to 0. And if you simplify, that is differentiation of I, Ra is Ra by V. Ra by V is constant, it is 1. And differentiation, WC and V are constant, differentiation of 1 by I is minus 1 by I square. If you multiply that, you will get WC by VI square. And equating to 0 and make the adjustment of the equation, that will be VV will get cancelled. It is I square Ra equal to WC. I square Ra, or as I is approximately equal to Ia, it is Ia square Ra. Hence, we can say generator efficiency is maximum when Ia square Ra is variable loss is equal to constant loss. When its variable loss is equal to constant loss, then generator delivers maximum efficiency. That means you have to apply the load such a way that its variable loss Ia square Ra is equal to constant loss, because Ia depends on I plus Ish, load current plus field current. Field current is constant, only load current, you have to apply the load such a way that Ia square Ra is equal to constant losses. Then you get maximum efficiency. From this equation itself, we can calculate the load current corresponding to maximum efficiency. That is, from the condition of maximum efficiency, that is I square Ra equal to Wc, where I is the load current. Then this equation will become the load current can be calculated under root of Wc by Ra. This is how we can calculate the load at which maximum efficiency will occur when constant loss and armature resistance are given. We can calculate at what load the maximum efficiency occurs. Next we'll see the voltage regulation of the generator. By definition, it is the change in terminal voltage of a generator between full load to no load is called as voltage regulation. It is usually expressed in percentage of the voltage at full load. That is, it is given by voltage regulation equal to VNL minus VFL divided by VFL into 100. It is VNL is the no load terminal voltage, VFL is the full load terminal voltage. Right? You know that as load increases, voltage drops. Right? That is, the voltage will change from no load to full load. If that change in voltage, if you express in terms of full load voltage, then we will get the regulation of the generator. Okay. Okay, a generator is said to be good when it has a minimum voltage regulation. That is, the change in voltage from no load to full load must be minimum to say the generator is good. That means it has less voltage drop due to armature resistance and armature reaction. That will give the less voltage regulation. Okay. Next, why we need to study the efficiency and voltage regulation? What is its importance? Efficiency indicates the power loss in the generator. That is, by the factor efficiency, we will come to know that the amount of power loss takes place in the generator, how efficiently the machine works. That idea we get from the efficiency. And as I already said, generator is said to be good if it has less power loss and more efficiency. Right? We previously said a generator will have as high as 95% of the efficiency. That means it has only 5% of losses. Right? Voltage regulation indicates drop in the voltage when generator is loaded from no load to full load. How much voltage drop takes place when you load the generator from no load to full load, that you know already. As load increases, armature reaction effect increases, voltage drop due to armature resistance also increases. That is, voltage drops. How much change in voltage takes place, how much voltage drops from no load to full load, that idea we get from the voltage regulation. Again, just previously I said, generator is said to be good if it has less voltage regulation. Right? So these both efficiency and voltage regulation helps to select generator for a particular application. Right? Again, that is, apart from the characteristic, this factor also helps to select the generator for a particular application. Again, suitability of the generator can be decided by knowing these two factors. Based on our discussion on efficiency and voltage regulation, we'll solve some simple problems. The first one is a 10 kilowatt 250 volt DC 6 pole shunt generator runs at 1000 rpm. When delivering full load, the armature has 534 lap connected conductors. Full load copper loss is 0.64 kilowatt. The total brush drop is 1 volt. Determine the flux per pole. Neglect shunt current. Shunt current, right? With the given data, we can calculate. Since the shunt current is negligible, there is no shunt copper loss. The copper loss occurs in the armature. So neglecting the shunt current, I is equal to IA, that can be calculated from the given data, that is output is given 10 kilowatt by voltage, that will be around, load current is 40 ampere, then armature copper loss is IA square RA. From that, armature copper loss is given 0.64 kilowatt, that is 640 watt. From that we can able to calculate the value RA. Then we know that the voltage drop is given, armature voltage drop is given by IARA. We know the value of IA, we know the value of RA, the armature voltage drop is 16 volt. And the brush drop, it is given in the problem, the total brush drop is 1 volt. Right? So for 2 brushes, it is 2 volt. So therefore generated EMF is equal to 250 plus 16, that is equal to V plus IARA plus brush contact drop, it is 267 volt. Again from induced EMF equation or generated voltage equation is equal to 5Zn by 60 P by A, we can able to calculate the value of phi. Substituting all other values, it will be around 30 milliweber. Okay. Next. A shunt generator delivers 195 ampere at terminal potential difference of 250 volt. The armature resistance and shunt field resistance are 0.02 ohm and 50 ohm respectively. The iron and friction losses equal 950 watt. Find EMF generated, copper losses, output of the prime mover, commercial, mechanical and electrical efficiencies. In this problem, it covers almost all the thing what you have studied previously. The given data are load current 195 ampere, V is given 250 volt, ISH is given 0.02 ohm, the armature resistance is 0.02 ohm and RSH is 50 ohm. The iron and friction losses are given 950 watt. You have to calculate EG, copper losses, output of the prime mover and 3 efficiencies. So we can calculate ISH for shunt generator. ISH is VSH by RSH. It is 250 by 55 ampere. IA is load current is given. IA equation of IA is I plus ISH. I is 195, ISH is 5, IA is 200. Armature voltage drop is given by IARA. IA, just now we calculated 200 into RA is given 0.02. So armature voltage drop is 4 volt. Then we know the voltage equation of the generator. Generated EMF is equal to V plus IARA. V is 250, IARA is 4 volt. So the EG is equal to 254 volt. So to calculate the copper losses is armature copper loss plus shunt copper loss. Armature copper loss is given by IA square RA. IA we calculated, RA is given. So armature copper loss is 800 watt. Shunt field copper loss is given by either ISH square RSH or V into ISH. Either formula we can use. V is given 250, ISH we have calculated, it is 5, it is 1250 watt. So the total copper loss is armature copper loss plus shunt field copper loss. It is 2050 watt. Stray losses are given, that is magnetic plus mechanical losses or the stray losses is given 950 watt. Total losses is, that is total copper loss plus stray loss, that is 3000 watt. Output of the generator we can calculate, that is V into I. Output is given by VI, output power. The voltage available at the output is V, load current is I, V into I is the output. V is 250, I is given 195 ampere, it is 48,750 watt. Input is output plus total losses. Output we calculated, total losses we calculated, that is 51,750 watt. So this is the output of the prime mover. Right? This is the output of prime mover. 51,750 is the output of the prime mover, that is input to the generator. Input to the generator. Right? So generator input is output of the prime mover, 51,750. Generator input minus stray losses is electrical power developed in the armature, that is 50,800. So now we got from that power stages, we got the value for A, that is input power to the generator, power B, power developed at the armature, C, that is actual output power available at the generator. Based on that, we can calculate mechanical efficiency, electrical efficiency, and commercial efficiency. Mechanical efficiency is B by A, power developed in armature by input to the armature or input to the generator. 50,800 divided by 51,750 into 100, it is 98.2. Electrical copper, that is electrical losses or copper losses are we have calculated just now, that is total copper loss 2050 watt. Subtracting that we get the electrical power is power developed at the armature minus this loss 2050 electrical losses, we get the output power, that is 48,750. Right? Electrical efficiency is output power by power developed in the armature. Power developed in the armature is its output plus this loss, that is C by B. P is power developed in the armature. We get 95.9. Commercial efficiency is output of the generator divided by input of the generator, that is output of the prime mover. Both we have calculated, 48,750 divided by 51,750 into 100, we get 94.2. So in this way we can calculate all the values asked in the problem. Next. Okay students, with the discussion what we had so far, based on that we will again do some exercises. So to test ourselves with the help of these multiple choice questions. Number 1, stray losses in a DC generator are the same as options: mechanical losses, magnetic losses, both A and B, none of these. You know that the stray losses are mechanical loss plus magnetic losses. So hence answer is C, both A and B add together. Next one, standing or constant loss of a DC generator are field losses of shunt generator, field losses of compound generator, stray losses, both A, B and C added together. The answer is D, that is standing or constant loss, field loss, field losses of compound generator and stray losses. All these comes under standing loss only. These all are the constant losses only. Stray losses, magnetic plus mechanical losses, both are constant. Field losses of compound generator, field losses of shunt generator. Next, out of the following 4 sources of losses in a DC generator, which one is minimum? Copper losses, hysteresis losses, eddy current losses, winding losses. Answer is, it's actually windage losses. Answer is D. Copper loss, hysteresis loss, eddy current loss. The windage loss is less. Overall, next one, fourth. Overall efficiency of DC generator is usually of the order of, we have just now studied, it is 85 to 95%. Fifth one, copper losses in armature of DC generator amount to which of the following percentage of full load loss? 5 to 10, 10 to 20, 20 to 30, 30 to 40. It is 30 to 40%. Answer is D. Next, sixth one. An ideal DC generator has regulation of option A 0, option B 20%, option C 30%, option D 40%. We have studied a generator is said to be good when it has very less generator. It is ideal generator which has no losses at all. So that means it is 0. The answer is A. Next, seventh one. Stray losses in a DC generator are same again. It is C. Mechanical losses plus magnetic losses. Eighth one. Efficiency of a DC shunt generator is maximum when stray losses are equal to copper losses, magnetic losses are equal to mechanical losses, armature copper losses are equal to constant losses, field copper losses are equal to constant losses. You know that efficiency is maximum when variable loss equal to constant loss. Armature copper loss, just to make you confused, questions will be asked like this. Armature copper loss is variable loss and constant losses. The answer is C. Ninth one, constant losses of a DC generator are defined as stray losses, field losses of shunt generator, armature losses of a compound generator, both B and C. Constant losses of DC generator, field loss plus field loss of shunt generator and armature losses of compound generator, both B and C. D. The hysteresis loss in a DC machine least depends on frequency of magnetic reversal, maximum value of flux density, volume and grade of iron, rate of flow of ventilating air. Hysteresis loss in DC machine, it does not depend on rate of flow of ventilating air. It depends on volume and grade of iron, right? Maximum value of flux density, frequency of magnetic reversal. I said according to Steinmetz, WH is given by B maximum to the power of 1.6, F, V and FV watts. That is volume, frequency and maximum flux density. The answer is D. Okay students, so far we have studied the total losses in the DC generator and various power stages, different efficiency terminologies used with the DC generator, voltage regulation and condition for the maximum efficiency. We solved some simple problems and you also try to solve this problem. A 20 kilowatt 440 volt short shunt compound DC generator has a full load efficiency of 87%. If the resistance of the armature and interpoles is 0.4 ohm and that of the series and shunt fields 0.25 ohm and 240 ohm respectively, calculate the combined bearing friction, windage and core loss of the machine. If you calculate, you may get the answer 725 watt. Students, try it. Okay. Thank you.